Welcome back to ECE 441A, 541A. Being returned are homeworks 4 and 5 and labs, lab 1. And if you turned in a soft copy, you probably won't see anything in the folder for your homeworks, but the labs, there will be material in there for the labs. I hope this comes as no shock that Friday we do not have class here. You are welcome to attend the breakfast, the engineer's breakfast. That's homecoming weekend. And I may actually put together some examples of working through some root locus to help you with your homework, which is due that day. Today what we want to do is actually cover rules 5 and 6, if we can get that far. We've already done where they start and stop on the poles and the zeros of the open loop transfer function. We know what segments of the real axis belong to the root locus. We know the angles that these branches approach by sketching the asymptotes, and we know where the centroid of those asymptotes are. We talked last time about the breakaway and reentry points on the real axis and how we could find that. That occurs at the relative max and the relative min, respectively, of the gain k along the real axis, where you have two branches meeting or coming together for breakaway and reentry. Today what we want to do is talk about or begin using rule number 5. And rule number 5 talks about where these branches, the point where they might cross over the imaginary axis. So we may see these asymptotes telling us that, oh, we've got something going off at 60 degrees and something going off at 300 degrees. Our branches are approaching those asymptotes. Somebody might ask us, where exactly did that branch cross the imaginary axis? Rule 5 says basically it's using one of our two conditions, magnitude condition and phase condition. It's using the phase condition. It's saying if I evaluated the phase on the imaginary axis and I find a point where the phase contributed by the poles and the zeros of the open loop transfer function is minus 180, then that point is where the root locus branches will cross, or branch will cross the imaginary axis. Branches of the root locus cross the imaginary axis if the phase angle condition is satisfied at that point. You need to get comfortable with calculating or determining angles from all of the poles and zeros to particular points in the complex S-plane. We'll be doing that in a design, or in the design process. Here it's telling us where the branches cross the imaginary axis. To get us started, to warm us up, why don't you get started? I'll give you a couple of minutes to sketch as far as you can go, and really you can get a pretty good rough sketch of a root locus for this transfer function g of s. It has 3 poles, and that's all I will say. And now I'll give you 2 minutes to sketch the root locus for that g of s. Go. we need more time? For those of you that are getting in a little after we started, I'm wanting you to sketch the root locus for this transfer function. How far did we get? Did some of you get the entire sketch? A rough sketch? Can you do it on the back of an envelope? Could you do it on a napkin for your mom over dinner? Could you sketch the root locus? Because I'm sure she's interested in that result. How do we start? What's rule number 1 tell us? Do we have these rules memorized? Or what's the first step in this process? Find the poles and zeros of your transfer function that's combined, the loop gain. Here we have just the g of s. We have a pole at the origin, a pole at -3, and a pole at -6. I'm hoping you at least made it that far. What's the next step? Now we cut bread, right? We're slicing the line, the real axis, into segments and identifying those segments that belong on the root locus. From 0 to plus infinity, does that belong? Yes or no on the root locus? Up or down? No? Okay. What about from the origin to -3? That one, thumbs up. From -3 to -6, up or down? Belong or no? Yes or no? Any sideway thumbs? Everybody's pretty, so from -6 to -infinity, that does belong to the root locus. Did we get further than this? Those are rules 1 and 2. How many branches do we have? How many root locus branches do we have for this system? Show of fingers. At the count of 3, I want to see fingers. I think they will fit on one hand. 1, 2, 3. I don't see very many fingers, but I do see some. It looks like 2 and 3. How do we determine whether it's 2 or 3? The number of branches that we have in our root locus. Those that are wanting to say 2, are you correct? And why are you saying 2? There are 2 segments, aren't there? There's 2 real line segments, but in fact, how many open loop poles do we have? 3. So we're going to have 3 branches. Each of those produce a branch. We have 2 branches between the origin and -3. they're coming together to look like one line segment. It is one line segment, but we do have two branches between 0 and -3, and those two are going to come together. We're leaving these poles, and Rule 3 allows us to determine where we are going to approach off-axis, if we're going to go off-axis, off the real line, and in what direction. Rule number 3 is going to tell us more information, and in particular, it tells us the angle that the asymptotes make and the centroid, or where we locate those asymptotes that are leaving the real line. What's our pole 0 excess? How many more poles do we have than zeros? 3. That's the key number, isn't it? P minus Z is 3, and we now can say that we have a fundamental angle of 180 divided by that pole 0 excess, and then we can multiply that by this counting variable, 2L plus 1, where L takes on values 0, 1, up to P minus Z minus 1, which in our case is 2. Which now says that we actually have 3 asymptotes. We have 60 degrees, we have 60 times 3, and we have 60 times 5, and those now are our asymptote angles for the different values of L. Here was L equals 0, L equal 1, and L equal 2. That's well and good, but we actually need one more piece of information in order to move forward with that data. We now know we're going off at 60 and 300 and 180. We sort of could guess the 180. We need the centroid. How do I compute the centroid? So I need to sum up my poles, subtract from that the sum of all of my zeros, and divide by that magic number, which is the pole 0 excess. I sum up all of my poles. I have a 0, I have one at -3 and one at -6. I take away all the zeros, I didn't have any, or I subtract the 0 locations, and I need to make sure that I'm paying close attention to where those are located. If they're negative or positive, that will impact the centroid. And then I divide by the pole 0 excess. Just coincidentally, the centroid is right on top of one of those poles, just because of the symmetry nature of those 3 poles, 0, -3, and -6. It's not, the centroid is not always going to be right at a pole. Don't be misled to be thinking that way. We now can sketch and that's why I told you you could bring your protractor to the next exam, so you could sketch these lines. This line asymptote is 60 degrees. This one is at 300 degrees, or at -60 degrees, and then our third one is going out to -infinity along 180 degrees. Did some of you get that far? So you found the asymptotes, you found where it was centered, and now you need to determine where these two branches, one coming from the origin, the other one coming from -3, they're coming together, and they are going to meet somewhere between those two endpoints and break off and approach those asymptotes as you adjust the gain k. If that third pole was not there at -6, and you just had two poles, they're going to meet right in between symmetrically and go off at plus and minus 90. But we have three poles. Where do they meet depends on the relative locations of those three poles, but we do know that they are going to approach those asymptote lines at 60 and minus 60 as we crank up the gain K. Rule 4. We're looking for a relative maximum of what? What are we looking at the relative maximum of? K, of the gain parameter K. We want to know how big is K going to be, and what's the relative maximum between 0 and minus 3. How do we find K? We use one of the two conditions, magnitude condition or phase condition. Magnitude condition, which says that we have K times G of S, H of S equaling 1. In our case, that's K over S, S plus 3, S plus 6 equaling 1. Now we can solve that for K, and we're interested in positive values of K, so I'm not going to show the absolute values on K, but we now have a quotient, or the absolute value of a quotient, that's the same as the quotient of absolute values. We're now looking at the lengths contributed by all of these factors. We now have K is equal to the length of S, the length of S plus 3, and the length of S plus 6. And we could numerically examine what K looks like for different values of S. At S equal to 0, what is K? You plug S equal to 0 in that expression for K, and what do you get? So you get, the last two give you a non-zero number, don't they? But that first one annihilates everything, doesn't it? You have zero distance from the origin to itself. K is actually 0 at the pole, which is what you would expect. We're starting our root locus at the poles. And now you might just say, well, just for sanity check, it better be 0 at minus 3, right? And it is. We're really interested in what's the value of gain K between 0 and minus 3, just to show you that it's not symmetric as far as how these branches approach each other. They don't come together uniformly necessarily as you increase K. Meaning the one at the origin may go over to minus 1/2, and the one at minus 3 may get closer or not so close relative to that 1/2 distance. What is the gain K at minus 1? Luckily, this isn't too hard to compute, is it? $10, isn't it? We have 2 times 5 times 1. What is it at minus 2? Now we have the absolute value of minus 2 is 2. Minus 2 plus 3 is 1, so we still have 2 times 4, or 8. Meaning it didn't take us as much gain to move us from minus 3 to minus 2 as it took us to get from 0 to minus 1. So we're not going uniformly towards each other. It zipped from minus 3 faster, in a sense, as far as the adjustment of K, towards the origin as the origin went towards minus 3. Well, in this case, it may be getting a little bit tedious to do that, so let's look at another way of finding the relative max. Let's use our calculus. We have just a cubic, which we can differentiate. Again, we're sort of playing with this absolute value of the product is the product of the absolute values. Let's just look at k being s cubed plus 9s squared plus 18s plus 18. Whoops. Getting carried away with my... So I multiply the last two, and I get s squared plus 9s plus 18, and then I just multiply by s. That is hopefully the expression for k. Now I differentiate that with respect to s. I'm trying to find the relative maximum of k between 0 and minus 3. I can factor a 3 out of those, and I now see that I have s squared plus 6s plus 6. I'm setting that equal to 0 to try to find my relative maximum. That's just a quadratic. That I can plug into my quadratic formula, and I find that I have two values that are real. One is at minus 1.3, and the other one is at minus 4.7. And now you're scratching your head and you're going, well, wait a minute. Do I have a breakaway at minus 4.7? No, you don't even have one of your root locus branches or either root locus branch at that location. So that one you can neglect. That's an extra relative max. The one that you want is the one between 0 and minus 3. Here's your relative max. And now we know precisely where that root locus is going to be branching off. It's at minus 1.3. And then it just goes, one goes here, and one goes there. And this point was the relative max at s equal to minus 1.3. Somebody might say, well, I want you to design your closed loop system such that you have two poles at minus 1.3 and the other one to the left of minus 5. How do you tell them what the gain is to get you to that point? Do we understand that these two poles, as we adjust the gain, or these three poles, as we adjust the gain k, are moving along these root locus branches? One is zipping off from minus 6 all the way to minus infinity. Hopefully we won't push it all the way to minus infinity. We might break something. But these two are going towards each other. We can now evaluate. We have an expression for k. What if we evaluate that expression at s equal to minus 1.3? That's where we want to get. We can just assign or find the gain k, and it actually ends up being 10.4. Now, suppose somebody says, okay, I didn't want my poles there. I actually want one of my poles to be at minus 1, s equal minus 1. Can you now find for them k to yield a closed loop pole at s equal minus 1? Do you now see how you can use this gain formula to find pole locations in your closed loop system? You say you want something to be right at minus 1. You can just evaluate this expression for k at minus 1, and we've already actually done that when we were looking before, but now we're doing it for maybe a different reason. You would have to crank up the gain to 10 to get you to that minus 1 location. Where's your other pole or poles? Roughly. We know that we're leaving the origin and approaching minus 1.3. We've now cranked up the gain to 10. We've gotten 1 to minus 1. The other one has to be to the left of that breakaway, doesn't it? It's somewhere probably between minus 2 and minus 1.3. Where's our third pole? It's going off to minus infinity, and so it's probably at minus 7 or something. It zips off maybe more rapidly than these two approach each other. Is that clear? Now what we want to do is maybe somebody says, well, where precisely does that branch, the upper branch, cross the imaginary axis? That's rule number 5. We know that it's somewhere between the origin, and we could do our trig to find where that asymptote crosses the imaginary axis. That's a 60-degree angle, and we know that one side is 3 units long. So we could find via an inverse tangent, the y, where that asymptote crosses the imaginary axis. And so pay attention. On some exams, I might ask you, where do the asymptotes cross the imaginary axis? Don't spend all your time trying to find where the root locus crosses. The asymptotes, where do they cross? That might be an easier question. Is that clear? So I might say, where do the asymptotes cross? We know that we're going to be probably close because those branches are approaching those asymptotes anyway. Let's now find, using rule number 5, where those branches actually do cross the imaginary axis. So with rule number 5, here's what I'm really doing. I have my poles and zeros if I had them. But what I'm doing is I'm looking at a particular point on the imaginary axis, and I'm determining the angles that these poles, and if I had zeros, where those zeros are relative to that location. Let me call this angle theta p sub 0. Let me call this angle theta p1, and this angle theta p sub 2. Rule 5 says that wherever that box ends up being located to give me those angles all summing to minus 180, that's where my branches would cross the imaginary axis. The phase angle condition then says that I have the sum of the zero angles. Those are in the numerator. Those are going to be all positive numbers, minus the sum of these pole angles. I'm subtracting all of these angles contributed by the poles. Those have to equal minus 180 degrees. In this particular example, I now have no zeros, so I'm just saying minus theta p0 plus theta p1 plus theta p sub 2 must equal minus 180 degrees. Is it clear what we're doing? If we had zeros sprinkled around, those zeros would contribute some phase. We would add those angles, subtract all of our pole angles, and the net effect, the algebraic result, needs to be equal to minus 180 degrees. Have we already talked, though, this semester about finding roots on the imaginary axis? Do you remember doing something, an array, somebody's name in an array that allowed us to find imaginary axis crossing. So there's many different ways to do this. We're trying to find where do the closed loop poles cross the imaginary axis? Well, the Routh array gives us that also. This would do it. Here we're sort of guessing where that box is going to be, but it's going to be close to where those asymptotes are crossing. So you could come down a little bit and calculate your phase from all three of those angles, or from all three of those poles. Is that clear? But let's now do it another way. Let's use the Routh array. Since we have these techniques, let's now start connecting those. In our example, the closed loop system, T of S, is this kg of S over 1 plus kg of S, h of S. Our h of S we didn't have, and we want this to be some numerator over a denominator. But remember, we have a ratio of ratios in that middle expression. We want to get rid of the denominators in the numerator and denominator so that we simply have a ratio of polynomials n over d. Or what I'm going to say, d of s is actually the numerator of 1 plus k g of s h of s. That makes, let me keep going, but I hope you understand what I'm meaning by that notation. This now says that I'm interested in the numerator of 1 plus k, for our example, s plus 3, s plus 6. Or I'm really saying put all of that over a common denominator, pull out the numerator of that ratio of polynomials, and that's what I'm going to be using because that governs my closed loop poles. Those are actually that's the d of s polynomial in my transfer function t of s. Or this is now equal to s plus 3, s plus 6 plus k. That's now my closed loop characteristic polynomial. When I set it equal to 0, it's my characteristic equation. And those values of s that satisfy that or let that go to 0 are the closed loop poles for different values of gain k. This is now, we've already done, this is s squared plus 9s plus 18, or this now says we have s cubed plus 9s squared plus 18s plus k, and this that's the characteristic polynomial, which when I set it equal to 0 will give me my closed loop poles. Meaning that's the expression I can now use in my Routh array. I now have a d of s that's equal to s cubed plus 9s squared plus 18s plus k. Are we clear where that came from, or why we found it in the first place? We're trying to find the gain or the values of s when they're imaginary. How many values of s do we have? 3. We want the 2 that will be imaginary. That third one's going to go off to minus infinity. But we want to find when does this have imaginary roots and find the k that causes that to happen. Really, we're more interested in the s values, the j omegas. We wanted to find where's our root locus crossing the imaginary axis. We can now create the Routh array. Hopefully we haven't forgotten how to do that. We can use our bookkeeping. S cubed, S squared, S1, S0. Here we have 1, 18, 9, and K. Did I start it correctly? I start the top row with the leading coefficient of the highest power of S, and then I just jump over powers of S to generate the first row. I step down one power of S lower. This time it's S squared, and I generate the second row. And now I create the S1 row. What's the S1 row going to be? Did everyone hear that? 9 times 18 minus K times 1 over 9. What's the S0 row? That's K, isn't it? How do we find the values of S right at the imaginary axis? Set the parameterized entries in the left column to 0. We don't need to set them all to 0, do we? We are looking for 2 roots that are symmetric with respect to the origin. If we have 2 roots that are symmetric with respect to the origin, that means we would be concerned with the S squared row determining our symmetry. And if we have symmetry in the S2 row, what row needs to be all 0? The one right below it, the S1 row. So we can set entries in the left column equal to 0. In this case, we only need to set the S1 row to 0. Is that clear? What we're doing now is we're going to force the S1 row to 0 to equal 0 by the choice of K. Now, just for grins, is K going to be bigger than 10? How do you know that? If you didn't already know the answer, if you hadn't calculated the gain K, but based on what we'd already done, we weren't even at the breakaway point with K equal to 10, were we? So we have to be at a bigger K to get to the imaginary axis. So if you calculate a number and it's less than 10, you go, uh-oh, I did an algebra mistake. Here, if we force the S1 row to 0, we're saying we have 9 times 18 minus K is equal to 0, or K is equal to 9 times 18, which is 162. So now it takes us, where did we break away? What value of K? 10.4. Now we went from 10.4 all the way up to 162 before we made it to that imaginary axis. So what's going to be the range of K for stability in this system? 0 to 162. Do you see how all of this is fitting together? Now if somebody says, oh, put in a gain of 170 because I know that's really going to make my steady state error small. You go, wait a minute. Don't crank it up to 170 because then you're going to drive your poles into the right half plane. You'll have an unstable system. You won't even have a steady state error. So you go, wait, why don't you keep it below 150 just to be on the safe side? Because we know after lab 1 and 2 that your model may not be that accurate that you've maybe experimentally determined. Maybe it's good, maybe it's not. But you have to live with what you can determine from the data. So now let's find the imaginary axis crossing. We found the K. How do we use that to find our values of s? That's the whole thing we were trying to do. So now we can plug that k into our characteristic polynomial if we wanted to. Then we would have 3 roots. We don't even have to go quite that far, do we? We can now use the Routh array. We can say at that k value of 162, S1 row is 0. I can now find the S squared row, what it's producing in terms of symmetry. I don't need to worry about the 3rd root. So now I can say, oh, from the S2 row, when k is equal to 162, we have S squared plus k equal to 0. We now have, whoops, the S squared row was 9 S squared plus k. Did everybody catch that mistake that I made? If you're not listening to the audio, the notes are correct. 9s squared plus k. We can now plug in, and I'm going to write k in a factored way. That was 9 times 18 before, so that I can now divide that 9 out more easily. And I now see that I have s squared plus 18 is equal to 0, or s squared is equal to minus 18. And now I know where my two branches of the root locus are going to cross the imaginary axis. Square root of 18 is, I can factor out a 9 inside the radical. That 3 can slide out, and I now have 3 times the square root of 2, so that I now have s equaling 4.243. Those are my 2 imaginary axis crossings, all from the phase angle, or from the Routh array. I could verify that with the phase angle condition, just to, as a sanity check. I can verify with the phase angle condition. Which, if I go back, I now have how many angles to compute? I have 3. I'll do the hard one. I'm going to calculate the angle of the pole at the origin. What's that angle? That's 90 degrees, isn't it? It's always 90, no matter what j or omega value I had. Theta p0 was 90 degrees. Theta p1 is now the inverse tangent of this 4.243 all over 3. So that's a little bit bigger than 45, isn't it? That now becomes 54.7 degrees. And theta p sub 2 is the inverse tangent of 4.243 over 6, which now that's less than 45. 35.3, so that if I now add those up, I have minus 90 plus 54.7 plus 35.3. Check. So we've now verified that those are, and if somebody was doing it the original way, hopefully you wouldn't stumble around too much. You would calculate the trig and say, there's where my asymptote crosses. You would maybe drop down a little from that and find out if you were close as far as where the branches cross. So now we have a good picture of the root locus, a pretty accurate picture. We now have These two come together at 1.3. They cross at J 4.2, whatever it was, 4.243, and minus J 4.243. And this point was S equal minus 1.3. Is that clear? Now you can label, maybe your sketch isn't that accurate, but at least you can label the points if somebody wanted to know. And you know the gain to get you to that crossing. This is at K equal 162. This is at K equal to 10.3. Is that clear? Let's now look at rule number 6, which we don't even need for that particular system. This is now concerning the angles of arrival and departure. This is when you have complex conjugate poles and or zeros. For example, suppose somebody gives you g of s equaling s plus 2 squared plus 2 squared over s squared s plus 4. And somebody just starts wanting to know, what's the root locus of this going to look like? Where are my poles and zeros? I have two poles at 0, so a lot of times I will actually just sort of offset those so that you see that I have more than one, but they're both right at the origin. Is that clear? That's the strategy that I will use. Do I have any more poles? I have one at minus 4. Where are my zeros? That factored polynomial in the numerator, I've intentionally written that way. That gives me zeros at minus 2 plus and minus j2. I now have zeros at minus 2 plus j2 and minus 2 minus j2. And now somebody says, okay, what's the root locus look like? And you go, what's your, now just go French bread. Slice up your real line. Which real line segments belong to the root locus? 0 to plus infinity. 0 to minus 4. Are you guys in a negative mood? Minus 4 to minus infinity. Yes, thank you. We now have this. What's our pole 0 excess? 1. How many asymptotes do we have? Just it's going off to minus 180. So somehow those two poles at the origin need to approach those two zeros. And will they do this? Will they do this? Will they do this? We need to figure out. That's the angle of arrival. We could also talk about the angle of departure at the origin. That's what Rule 6 will allow us to do. So we'll pick up at that point, but what do you think we're going to do now that I've already dismissed you? We're going to compute the angle close to that 0 upstairs, and it has to have, the net angle needs to be minus 180. We'll use that to figure out how we're approaching that 0.